Okay, so this is going to be the first video of a series of videos that deal with optimization. And optimization is looking for, well, I would say like the most optimal case, but it's not good to define a word using its word, but like a best case scenario. What's in the superlative case? And if you put it into a context, like maybe it's like what's the biggest, what's the cheapest, what's the most money I'm going to make, what's the least amount of time it's going to take. So you're trying to optimize or trying to find the most ideal situation in a given context. And so I've got a lot of different examples, and so I kind of want to maybe take a look through some of them here. And so I have this rectangle inscribed underneath a parabola, and I want to know what is the largest possible area, right? What's the biggest area that would fit under that parabola? And there are lots of different rectangles you could pick, right? I just picked one, but maybe you think it should go a little bit flatter and go wider like that. Like, does that have more area than the orange one? Or maybe you should, pick one that is just a little bit taller, like here. Maybe that one has the most area, or maybe it's somewhere in between, and so the question, or maybe this is the most area. So the question is like, how can I efficiently find something that's the most area without actually always having to calculate, oh, how much is this area? How much is this area, right? So what we're going to do is we're going to think about, well, this rectangle, just area is base times height. So I know at least I can come up with a formula that says, well, area of that rectangle is base times the height. And if we're going to define it based on this arbitrary point x comma y, then that means this distance here is x, because I went to the right x, but it's symmetrical over the y-axis. So that distance also is going to be x. So together, the base of that rectangle, right, this rectangle's base, this right here, will be called 2x. Okay, so with that color and thin. So I know the base is 2x. And my height is y. But remember, every y value could be written as this particular function. So negative 1/2 x squared plus 8. So I can get an equation that represents area. My area is equal to, well, let's see, if I distribute, that would be just negative x cubed, because 2 times half would cancel, plus 16x. That looks like a terrible 16. Let me erase that and try again. Plus 16x. There we go. Okay. So now the thing is that this represents all possible areas. So as soon as I choose, like, let's let x be 1, I'd know the area, right? So like when x is 1, I could even just do a table of values here, x and then the area of x. So when x is 1, if you put 1 into this equation, you would get negative 1 plus 16. So 15, you get an area of 15, but then maybe you let x be 2. Right, so let x equal 2, so go a little wider. 2 cubed is 8, so there's a negative 8. But then 16 times 2 is 32, so you have 32 minus 8 is 24. So now I got a bigger area, and then you could try maybe 3. 3 cubed is 27, so you have negative 27, plus the 3 times 16 is 48. And so that's going to give you 21. So you're like, oh, so maybe this is the biggest area, or maybe it's somewhere in between 2 and 3, right? Or maybe it's in between 1 and 2, and this is on the way down. So again, we're trying to find a way to find, efficiently find what's the biggest area. And so if I were to graph this, like you think about like a cubic function, it's it's a negative cubic, and I know it goes through 0, 0. So, something like this, or actually it could be probably something like this. Sorry. Oh, the pen is not working. There we go. Something like this. There it is. This graph represents all possible areas. There's got to be some maximum value on that graph. And that's where we're going to use calculus, because I know something about that maximum value. It's a critical value because its derivative, aka the slope of the tangent line, 0. So I kind of gave you a lot more background of why we're doing derivatives here and kind of setting this up. You don't have to do this each and every time. Like once you have an equation and something that relates the area to its variable, then just take the derivative. So call it a prime and set it equal to 0 because it's a critical value. So negative 3x squared plus 16. So we know that it's never undefined, guys. It's a polynomial, so we don't have to worry about those as critical values. So we set it equal to 0, and we solve. So let's add 3 over. So 3x squared equals 16, and then we could divide by 3. So x squared is equal to 16 thirds. So then x would equal, now technically it would be plus or minus square root of 16 is 4 over the square root of 3. But since we're in the first quadrant, we know our x would have a positive value. So we know that our x is going to equal 4 over root 3. That value of x will generate the largest area. Now, that isn't the largest area. That just is when it happens. It happens when x is this value. What is that area? We'd have to evaluate it by putting it into this formula and calculating that. So then I could say, okay, well, that area is equal to the opposite of 4 over root 3 cubed plus 16 times 4 over root 3. Well, 4 cubed is 64. And then root 3 cubed would be 3 root 3. For some reason, my pen is not working. Oh, and now my brain is not working. Sorry about that. Erase that. We said 3 root 3. So negative 3 root 3. And then plus, and then 16 times 4 is also 64 over root 3. So really, I mean, you could think about this. This is like a negative 1/3 of 64 over root 3, and this is a full amount of 64 over root 3. So, and what you end up getting is 2/3 of the 64 over root 3. That's how you would have gotten if you found the common denominator too, which is 128 over 3 root 3. And that's fine. You can leave it like that. You can rationalize it. I don't really care at this point, but that's the biggest area. So that would be the largest area I could put underneath that parabola. This is the y value. This is the x value. The when is the x. The what is the y coordinate. Okay, so and the concept is similar in terms of taking a derivative and and trying to find that function and then setting equal to 0. Okay, so let's look at this problem. You have 900 meters of fence to enclose these 5 pens. Write an equation to represent the area of the space. So I want to think about, like, I've used up x here and x here and x here and x here and x here, right? And I would label this x and this x and this x and this x because that's a rectangle. So they're equal sides. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've used up 9 x's so far, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And I've got 900 units. What is it? 900 meters of fencing. So if I think about, I need to equally just like I need to take 900. Oops. Erase that. 900 minus 9x. Or I could think about it this way too. Why don't I do this? Oh my goodness, my pen is just malfunctioning. We could also call this distance here y. And then there's another distance there of y, another distance there of y, another distance there of y, and another distance there of y. So 1, 2, 3, 4, 5. So I have 5 y's and I have 9 x's. So I have 5 y's and I have 9 x's. And that together has to add up to 900 for my perimeter. But then I can solve for y in terms of x. So I can say, well, 5y is equal to 900 minus 9x, divide by 5. And so was it 180, I believe, minus 9/5 x. So at least I know what this y value is in terms of x. And to write an equation of the entire area, what it's referring to is like the entire enclosed space, right? It's this whole area right here. And so how do I find that area? Well, it's just a rectangle, just like the last example, right? It's a rectangle. So I know my area is equal to y, okay, times this height here. And what is that height? It's 1, 2, 3. This time it's 4x. So my area is equal to 4xy. And we already know what y is, so let's substitute that in. And so our area is equal to 4x times 180 minus 9/5 x. So let's go ahead and multiply that through. So that's 720x minus 36 over 5 x squared. Now, this right here represents all possible areas, depending on what x you choose. So you could choose x equals 1 and figure out what that area is, or x equals 2, or x equals 5, or whatever. Or we could realize that this, if I were to graph this is actually a quadratic, and the fact that the lead coefficient is negative means somehow it's opening downward, which means at some point there's a top value, right? And so I want to find that. And it's so, like, I actually do this exact same problem in honors pre-calc, but they don't know calculus, but they know how to find the vertex, right? So we could use that and find the vertex and understand that, or we could go much quicker and find, we could find out what that is by using calculus. So let's go ahead and take the derivative, set it equal to 0, because we know the slope of the tangent line at that vertex is 0. So let's do that. And I was just reminiscing about honors pre-calc. If you had me in honors pre-calc, you know that I did not let them use opposite b over 2a. I made them complete the square. It's one of my favorite things to do. Okay, so derivative, 720. And then minus, and then that would be 72/5 x. And since it's a quadratic, it's never undefined, this derivative, which is now becoming linear. So then we set it equal to 0 and we solve. So 720 minus 72/5 x. We could add that over. So 72/5 x equals 720. And then multiply by the reciprocal, which is the same thing as dividing by that coefficient. So 720 over 1 times 5 over 72. And actually works out nice, because the 72 would cancel with this to be just 10. And we get 10 times 5, so we get x is equal to 50. Now that just is the when. It is asking for what is that area, right? What is the area? So then we would just have to substitute 50 into our area formula, which is right here. Right? So we could substitute 50 into that, or this version here. It doesn't really matter. I'm going to put in this version because I think it's easier, but that's just me. So let's put 50 into that. Oh, sorry. I want to go back to the pen. There we go. So area is equal to 4 times 50 times 180 minus, and if I put 50 into x, that would be 9/5 of 50, which actually becomes 90. And so 180 minus 90 is 90. So we get 4 times 50, which is 200, times 90, which is 18,000. So there's my maximum area, 18,000 square meters, I believe, which is a lot of area. Okay, now, again, I want you to realize this process. You find the equation, you take a derivative, because that derivative will represent your critical values, which have like tangent lines that are 0 sloped, and that's going to be the location of that highest value, of that maximum value. Okay, so let's just do one more in this video, and then I'll do it the next video. But number 3 is like just the bare bones of what we just did, no context. And I've seen this question on multiple choice, so I've just removed the multiple choice. Like they're telling you, hey, let's find the minimum product of 6xy. So you say, okay, well, here's my product, 6xy, and then they already tell you what y is, right? So 6x times 3/4 x then minus 1. So you can distribute. So that's 18x squared over 4 minus 6x. And if you wanted to reduce, certainly you could. The product would be equal 9/2 x squared minus 6x. And again, this is a quadratic function. We did this in honors pre-calc, actually. And think about, what does this quadratic look like? Because it's a positive leading coefficient. There we go. And my pen does not want to write on that side of my on my smartboard for some reason, or at least on my tablet. Try again. There we go. So this quadratic, whatever it looks like, right? Definitely has, because it's opening up, definitely has a minimum value. And that's exactly what I'm looking for, right? The minimum. So I could either find the vertex or take the derivative and set it equal to 0. And so let's do the derivative. So p prime is equal to 9x, because, right, the 2's cancel, minus 6. Now that's linear. It's never undefined. So we said 0 is equal to 9x minus 6. And we can solve to figure out that x is equal to 2/3. So when x is 2/3, whatever that value is, then we'll get the biggest product. So we do need to substitute the 2/3 back in, and you could put it in any variation of the equation. I like it in this form because it's factored. It just, to me, makes it easier. So then I'll go ahead and substitute 2/3 in. So product is equal to 6 times 2/3, and then parentheses 3/4 times 2/3 minus 1. And so then that's equal to 4 on the outside. The 3's cancel. So we get basically 1/2 minus 1, which is negative 1/2. So 4 times negative 1/2, which is equal to negative 2. So that right there is the y coordinate, and that would have represented the smallest product, negative 2. Okay, so and again, I'm just going to go through all of the examples. So the idea maybe is that by the next video, or even maybe by this video, you might be able to tackle a problem. Say, hey, I kind of understand this. Let me try to set it up by myself, and then maybe just go to the end and check it. But the thing with these questions, and it's just like when we did related rates. Like every problem could be slightly different, and it takes time to go through and for lack of a better word, be exposed to the different kinds of questions, so they become familiar with the different, those different contexts. But the process is the same. You create the equation, you take the derivative, is it undefined, set equal to 0, and if necessary, checking the endpoints, because those could also be maximums or minimums.